In today's lecture, I will talk about binary star, neutron star, black hole and accretion disk. I am Sudip Bhattacharya from Department of Astronomy and Astrophysics of Tata Institute of Fundamental Research, Mumbai. In the first part of the lecture, I will give a very brief introduction of binary star, neutron star and black hole. In a binary stellar system, two stars or any two massive bodies rotate around each other due to gravitational interaction. For example, here there are two stars, one with mass m2 is a smaller mass star, while another with mass m1 which is a larger mass star, and all these lines are showing equipotential surfaces of this binary system, and I will describe that now. In a coordinate system co-rotating with the binary, there is pear shaped equipotential surface around each component like this and this due to the combination of gravitational and centrifugal forces. Going outwards from the two mass centers, at a certain value of potential, these two surfaces touch each other at the first Lagrangian point L1 located on the connecting line of the centers of the two components as shown here. This figure of 8 in bold lines is called the Roche lobe, and here is the touching point which is the inner Lagrangian point or L1. As I said, this critical equipotential surface, that is this figure of 8, is called Roche lobe. When the secondary, that is the normal star, fills its Roche lobe, that is this is the secondary or normal star of mass m2, when it fills its Roche lobe, this volume, and matter comes up to this point L1, matter from it flows towards the primary, which could be a neutron star or even a black hole, through the L1 point due to unbalanced pressure, as at L1 there is a potential maximum along the line connecting two mass centers. So, when the secondary star fills its Roche lobe, matter from here flows towards the primary star, which can be a neutron star or a black hole, because here at the L1 point in this direction connecting the two masses is a potential maximum. In the Roche lobe of the primary, forming an accretion disk, this matter finally falls on the surface of the neutron star or it goes into the black hole, and this matter emits X-rays. This type of mass transfer is called Roche lobe overflow. As the wind from a low mass star, which we are considering here, is not strong, we neglect the accretion from stellar wind and take Roche lobe overflow as the only mechanism for mass transfer in this particular case. Now, here I show only the Roche lobe of both the stars. This is the Roche lobe of the secondary star, it is filled up by the secondary star and matter is flowing towards the primary star, and an accretion disk is finally formed. How is that disk formed? I will say a few words about that now. Note that this B1 is the distance between the inner Lagrange point L1 and the primary star. So, when the matter from the secondary star comes out of its Roche lobe, here is the L1 point, like here, the matter in a stream flows towards the primary star, which could be a neutron star or black hole, forms first a ring of matter around this star and then finally forms a disk, and then it is being accreted. How does it happen? The matter coming through L1 towards the neutron star possesses some initial angular momentum due to the orbital motion of the secondary. This matter will lose some energy by dissipative processes and attain the lowest possible energy for that particular angular momentum, hence is expected to be rotating in a circular Keplerian orbit around the neutron star or the black hole at a distance r arc from the center of the primary. So, it forms a ring of matter at a distance r arc from the primary star, and this r arc will be given by, due to the angular momentum conservation, by this equation r arc into v phi equal to b1 square into omega, where v phi is given by this formula, where m1 is the mass of the primary star and omega is the binary angular frequency. B1 can be seen from this figure. But dissipative processes will be going on in the ring of matter at r arc, resulting in the loss of energy and redistribution of angular momentum. Now, the Keplerian angular momentum increases outwards, and therefore, if this matter has to go in towards the primary star, it has to lose angular momentum. How does it do it? Most of the particle will orbit closer and closer to the neutron star or the black hole, losing their angular momentum, and this extra angular momentum will be taken away by few particles which will go outwards and will gain angular momentum. Thus, the initial ring of matter will spread out and will form a disk, as the radial speed of a particle is negligible compared to its transverse speed. Thus, an accretion disk is formed. I will now say a few basic words about neutron stars and black holes. A neutron star is created when a massive star dies by a supernova explosion and its core collapses, like here. At the center, a neutron star is created. A neutron star is a dead star, that is, there is no fuel burning is going on like a normal star, but it is more alive than a normal star in certain ways. A neutron star is an extreme object because more than one solar mass is crammed into a sphere of the size of a city. Here is a cartoon of a neutron star in comparison to a city. The typical radius of a neutron star is between 10 to 20 km. The mass is between 1 to 2 solar mass. The core density is of the order of 5 to 10 times the nuclear density. Depending on the kind of neutron star it is, the magnetic field could be between 10 to the power 7 Gauss to 10 to the power 15 Gauss. And the spin frequency of some of the neutron star, which we call millisecond pulsars or fast spinning neutron stars, can be between 200 and 700 Hz, that is, the neutron star spins around its own axis 200 to 700 times in just 1 second. But there are other neutron stars which spin much slower. Some of the most extreme conditions in the universe exist in neutron stars. The neutron stars are important for many points of view. For example, they have many incarnations. They emit in all electromagnetic wavelengths from radio to gamma rays. They are important for multi-messenger astronomy, for example, electromagnetic radiation, neutrino, gravitational waves, and they are important for several branches of physics and many branches of astronomy. Here are some examples of various neutron star systems which are observed in X-rays. For example, here is a real image of Crab pulsar in X-rays, where at the center is the neutron star. Here is an X-ray image of the Geminga pulsar, which is an older pulsar which is speeding through the interstellar medium, and we can see its bow shock as well as the pulsar itself. But the systems we are interested in for this lecture are low mass X-ray binaries, that is LMXBs, and high mass X-ray binaries, that is HMXBs. In a low mass X-ray binary, a neutron star here accretes from a low mass star, while for a high mass X-ray binary, the neutron star accretes from a high mass star. Now a few words about black hole. A stellar mass black hole with a mass of the order of 10 solar mass is created by the collapse of the core of a massive star when it dies and can be found in an accreting binary system. Supermassive black holes are found at the center of galaxies. A stellar mass black hole is also created by the collapse of the core of a massive star. A black hole does not have any hard surface. The entire matter is collapsed essentially into a point which could be a singularity or which could be a quantum ball of Planck length, and this matter hides behind an horizon called event horizon. This is an invisible surface from inside which nothing, not even light, can escape, and hence the name black hole. So, we cannot see a black hole directly, but when matter falls into a black hole, for example through accretion, then we can see this matter, and thus we can essentially observe a black hole. Neutron stars and black holes are unique laboratories, and here are some examples. On the left side, I talk about only neutron stars. The question is, what are the properties of the relatively cold matter at a density 5 to 10 times the density of an atomic nuclear? This is the density at the core of a neutron star. We cannot find the answer of this question by doing experiments in terrestrial laboratories, and for answering this fundamental question of physics, we have to observe a neutron star. For example, is the neutron star core a bag of 10 to the power 57 free quarks, or are there new types of particles in the neutron star cores? To answer these questions, we need to measure the mass and radius of the same neutron star. Neutron stars and black holes are both extremely important to probe the strongest, possibly the strongest gravity in the universe and the flow of matter in this strong gravity. In this particular plot, we have placed many objects in the universe, and this plot shows their strengths of gravity. Along the x axis of this plot is the parameter gm by r, while m is the typical mass of a particular object and r is its radius, while along the y axis we have placed gm by r cube. The x axis parameter, that is gm by r, is a measure of gravitational potential, while the y axis parameter is a measure of the space time curvature. Both gravitational potential and the space time curvatures are measure of the strength of the gravity. And here in this plot we have placed various objects. For example, here is our solar system, here is a main sequence star, for example our sun, here is a white dwarf, here is our earth, here is our Milky Way galaxy starting from here going up to this, from the edge of the galaxy up to the central supermassive black hole. Here are possible intermediate star black holes, and here are neutron stars and stellar mass black holes. And note that each axis is in the logarithmic scale. Therefore, the neutron star and stellar mass black holes have by far the strongest gravity in the universe, and therefore, these objects are extremely important to test a law of gravitation like the general theory of relativity and the flow of matter in this very strong gravity region. Neutron stars and black holes are unique laboratories for many other reasons, and here are a couple of more examples. For example, study of super strong magnetic field of neutron stars. The magnetic field of the neutron star can be up to of the order of 10 to the power 15 Gauss, and we cannot create anything near that in our terrestrial laboratories. So, to understand the physics of such a strong magnetic field, we need to observe neutron stars. On the other hand, black holes are possibly the simplest objects in the universe, characterized by only two parameters, mass and spin, and therefore, it is extremely important to measure the mass and spin of black holes to understand their properties and probe the strong gravity. In the second part of the lecture, I will talk about the measurement procedure or measurement technique of the component masses of a binary system. In the binary system, two massive bodies rotate around each other due to gravitational interaction, and these massive bodies could be two stars including neutron star or black hole, or a star and a planet. Now, look at this picture. Here are two massive bodies with masses m1 and m2 rotating around their center of mass Cm. The separation between the two bodies is a, and m1 is r1 away, r1 distance away from the center of mass, while m2 is r2 distance away. Therefore, from this figure we can write r1 m1 equal to r2 m2, a equal to r1 plus r2, and therefore, r1 equal to m2 divided by m1 plus m2 into a, and r2 equal to m1 divided by m1 plus m2 into a. Therefore, the equation of motion of the mass m1 can be written as this by equating the centrifugal force to the gravitational force like this: m1 into omega square r1 equal to g m1 m2 divided by a square, where omega is the angular speed or angular frequency of each mass around the center of mass. Putting the value of r1, we get omega square equal to g into m1 plus m2 divided by a cube, which is the well known Kepler's third law. Now, as an example, let me mention how we use this to measure the solar mass from the known solar distance. So, if we assume, and this is a reasonable assumption, that we neglect the Earth's mass compared to the solar mass, then in this Kepler's third law we have only the solar mass here in the numerator. The angular speed omega is measured from the known orbital period of 1 year, and suppose we can measure a, that is the distance between the earth and the sun, then we can easily measure the sun's mass, which comes out to be of the order of 2 into 10 to the power 33 gram. This is a way to measure the solar mass. Now, let us consider a visual binary system. Let us see this picture. where this is the center of mass. Around it two masses m2 and m1 are rotating. This is same as this picture that I showed earlier, but now in the face on view, where the observer inclination angle is along the perpendicular direction to the orbital plane. For such a visual binary stellar system, both the stars are directly seen, and therefore we can directly measure the omega A, which is R1 plus R2, R1 and R2 from the observed orbital period, the known distance of the source and the angular separation between the two ends of each star's orbit. And then from R1 M1 equal to R2 M2 and Kepler's third law, both M1 and M2 can be measured. So, for a visual binary, when we can see both the stars directly, we can measure both the masses relatively easily. But we are not always fortunate enough to directly see the stars, and we can see them or we can observe them only through their spectrum. That is, we can measure the spectrum of each of the stars, and such binaries are called spectroscopic binaries. Here look at this figure. This is same as this figure that I showed earlier. This was earlier in face on view. Now it is a more general inclined view, where the inclination angle I measured with respect to the perpendicular direction to the binary plane can have any value, and therefore the orbits look like ellipses, although they are actually circular. In such a case, for a spectroscopic binary, A, R1 and R2 cannot be measured directly. Only line of sight velocities and the orbital period, and hence omega, can be inferred from the observed periodic Doppler shift of spectral features and lines. How can we do this? As I mentioned that in a spectroscopic binary, we can measure the spectrum including the spectral features and lines of both the stars, if we are fortunate enough. Suppose we consider this star with mass m1 and we measure its spectral line, one of the lines. As the star follows its orbit, sometimes the star goes away from the observer, that is us, and sometimes it comes towards the observer, and therefore there is a Doppler shift of the spectral line which is measured, and this shift changes with the orbital period, with the orbital phase, and we can measure the speed of the star from this periodic variation of the Doppler shift of the spectral line. But we cannot of course measure the actual speed or actual velocity of the star. We can measure the speed only in the direction of our line of sight. So, these are the 4 locations 1, 2, 3 and 4 for the star M1. Similarly, for the star M2, these are the 4 locations 1, 2, 3 and 4, and corresponding to these locations in the orbit, which corresponds to the time or orbital phase, we can measure these velocity curves from the Doppler shift of the observed spectral lines or features, and the amplitude of this curve gives V1 mod V1 sin I, where I is the inclination angle and V1 is the velocity of the star of mass m1. Similarly, from this amplitude we can measure mod V2 sin I, where V2 is the actual velocity of the star of mass m2. So, what we can observe is V1 obs, mod V1 obs and mod V2 obs, which are given by these relations. Now, note that mod V1, that is the magnitude of the actual velocity of the star of mass m1 is omega r1. So, r1 is the distance of the mass m1 from the center of mass. Similarly, mod V2 equal to omega r2. Now, from the variation of the Doppler shift, from the variation of the energy or wavelength of the observed spectral lines, we can easily measure the orbital period and hence the angular speed of the stars, which is omega. Now, if we take ratio of these two, we get using this relation V1 mod V1 obs divided by mod V2 obs equal to m2 by m1. The left hand side is the measured quantity, while right hand side m2 and m1 are unknown parameters which we want to measure. Now, from above, that is this relation, and from the Kepler's third law, m1 plus m2 into sine cube I equal to tau into mod V1 obs plus mod V2 obs whole cube divided by 2 pi g. Here tau is the orbital period which is known, V1 obs and V2 obs are also measured. So, right hand side is a measured quantity, and on the left hand side there are three unknowns m1, m2 and I. Therefore, we have two equations and three unknowns, and therefore, we cannot measure from these for the spectroscopic binary, we cannot measure m1 and m2 separately. We can measure a combination of them, but we cannot measure m1 and m2 separately unless we know the value of the inclination angle I. Of course, we can put a limit on m1 plus m2, but we cannot measure them separately without knowing the value of I. Now, in certain cases I can also be estimated. For example, if the binary system, that is the spectroscopic binary, is an eclipsing binary, implying that the inclination angle is close to 90 degree, then assuming this high value of I, we can measure or we can estimate the two masses m1 and m2 separately. For an eclipsing binary system, one star periodically blocks the other star from our line of sight, and that can only happen if the inclination angle I is very high, that is close to 90 degree. If we are fortunate enough to have an eclipsing system, then we could measure even for a spectroscopic binary the two masses separately. For a spectroscopic binary, we are often much less fortunate, and we can measure the velocity curve of just only one star or one object. That is, we can possibly measure only V1 obs, but not the V2 obs. And then we have only one equation given here, that is m2 cube divided by m1 plus m2 whole square into sine cube I equal to tau into mod V1 obs cube divided by 2 pi g, but we have three unknowns. This could happen when the other object, for example, is a planet or a faint star, and we cannot measure its velocity curve. What can we do from this one equation and three unknowns? Here is an example. If the object of mass m2 is a planet, then m2 is less than m1, and we can neglect this m2 compared to m1. Suppose m1 is the stellar mass which is known from say the spectral type, that is independently. We can take m1 square from here to the right hand side, and in this case the entire right hand side is known on the left hand side there will be m2 sin I. So, in such a case we can measure m2 sin I, and m2 is the mass of the planet in the system. Now, since we do not know I, we cannot measure the mass m2, but note that the upper limit of sin I is 1, and putting that we can get a lower limit of the planet mass m2. So, this is how even when we have just one equation we can measure the mass of the planet. Now, consider this single equation, but three unknowns, that is the same equation. We can write the equation in this way: f of m2 equal to m2 into m2 square divided by m1 plus m2 whole square into sin cube I, where from here we have taken one m2 out, but the equation remains same, equal to the same value equal to C, where Fm2 is called the mass function of the object with mass m2, and C is a measured quantity because both tau and V1 obs are measured. So, Fm2, that is the function of mass m2, is measured, and this is equal to this. Now, notice that sin cube I is less than or equal to 1, and m2 square divided by m1 plus m2 whole square is less than or equal to 1. Therefore, from this we get m2 greater than or equal to function of m2 or f of m2. We can measure f of m2, it is a measured quantity as can be seen from here, and this can be measured even when the velocity curve of just one object is measured and the inclination angle I is unknown. So, even when we have just one equation and three unknowns, we can measure the lower limit of m2 relatively easily from this. This is very important for neutron stars and black hole mass measurements. For an accreting compact object, that is neutron star or black hole, this is how we can measure the lower limit of the compact object mass. And if this mass comes out to be sufficiently more than 3 times the solar mass, we conclude that the compact object is a black hole, because a neutron star mass cannot be much higher than 3 solar mass. And this is a standard way to detect a black hole, and this was the first time a black hole was first roughly confirmed by measuring its dynamical mass, which came out to be much higher than 3 times the solar mass. In this third part of this lecture, I will briefly describe a basic theory of an accretion disk. This is an image or a cartoon of an accretion disk. Here we consider the standard model of steady, geometrically thin, optically thick accretion disk in Newtonian gravity. That is, the disk is not changing with time, that is steady. Geometrically thin means its height is small compared to its radial extent, and optically thick essentially means that it emits as a black body. So, as long as these conditions, these criteria are satisfied, the theory I will describe now will be valid, whatever the central accreting object is, but I will generally consider a neutron star as the accreting object. In a thin accretion disk using cylindrical coordinates r theta z, we expect that the theta component v theta should be the main component of velocity and the z component v z equal to 0. That is, there is no motion of matter in the direction perpendicular to the plane of the disk. the accreted matter should move around the neutron star with a nearly Keplerian speed as shown here, where m is the mass of the neutron star or the accreting object, and a small radial inflow, that is Vr is less than v theta, that is the accreted matter is moving in almost a circular orbit around the central object, and it is slowly losing its angular momentum and is coming towards the central object. Therefore, Vr, that is the radial speed, is less than the angular speed v theta. We consider del theta equal to 0 because of the theta symmetry of the system. Then the equation of continuity, that is the conservation of mass, is del sigma del t plus 1 by r del r of r sigma Vr equal to 0. This is equation 1, where sigma is the surface density of the accretion disk, that is the mass of the accretion disk per unit area. Using this and the theta component of the Navier-Stokes equations, which gives the angular momentum conservation, we get del t of sigma r square omega plus 1 by r del r of sigma r cube omega Vr equal to lambda, where omega equal to v theta by r, that is the angular speed, and lambda is the term involving viscosity. We note that 2 pi r dr sigma r square omega is the angular momentum of an annulus between r and dr. This is because the circumference of this annulus is 2 pi r, its width is dr. So, the total area is 2 pi r dr, and then we multiply it with the sigma surface density of mass, and we get the total mass of this annulus multiplied by r square and omega, we get the angular momentum. Hence, equation 2 given here multiplied with 2 pi r dr shows how the angular momentum of the annulus changes by the viscous torque. Therefore, lambda equal to 1 by 2 pi r dg dr, where g of r is the viscous torque at the radial distance r. Here is a cartoon of an annulus in the disc between the radius r and r plus dr, and we see that outside this annulus and inside this annulus are the viscous torque values are different, and therefore, there is a net torque on this annulus, and that is how the angular momentum is transferred and matter is accreted. It is normally assumed that the term dv theta dr gives the velocity shear. However, for the accretion disk, dv theta dr is omega plus r into d omega dr, in which omega is associated with pure rotation, and therefore, only the r d omega dr part gives the shear. Therefore, the viscous stress is mu r d omega dr, where mu is the coefficient of viscosity. Then the viscous torque is given by g of r equal to 2 pi nu sigma r cube d omega dr. This is equation 5. Here nu equal to mu divided by rho is the kinematic viscosity and rho is the volume density. Therefore, using equations 2, 3 and 5, we get the equation 6 given here, which comes from the angular momentum conservation. Therefore, equation 1, which is the mass conservation, and equation 6, which is basically the angular momentum conservation, govern the accretion disk dynamics. If the disk is nearly Keplerian, then these two equations can be combined to get the equation 7, that is del sigma del t equal to 3 by r del r of r to the power half del r of nu sigma r to the power half, and this is the main equation of a thin accretion disk. This equation gives the time evolution of the accretion disk. But we are interested in this lecture in a steady accretion disk, that is del t equal to 0. Therefore, putting del t equal to 0 from equation 1 and from equation 6, we get R sigma V r equal to C1, which is essentially the mass conservation, and sigma r cube omega V r minus nu sigma r cube into d omega dr equal to C2, which is essentially the angular momentum conservation, where C1 and C2 are constants. For a steady disk, the mass accretion rate is small m dot equal to minus 2 pi r sigma V r, where V r is the radial speed. Therefore, from equation 8 given here, we get C1 equal to minus m dot by 2 pi. So, we have derived one constant of integration, that is C1, in terms of an observable, that is the mass accretion rate. In order to calculate the other constant of integration, that is C2, we consider a boundary condition, that is d omega dr at r equal to r in, that is at the disk inner edge, equal to 0. Let us now justify this condition, this boundary condition, for the following two cases. This boundary condition, that is d omega dr equal to 0 at the disk inner edge, and the two cases are when the disk is extended up to the stellar surface and when the star is well inside the disk and the matter falls from the disk inner edge towards the star quasi radially. For a near Keplerian disk, the angular speed omega increases with the decrease of r. This comes from the formula for a Keplerian disk. For the first case, that is when the disk extends up to the stellar surface, since the stellar angular speed is less than Keplerian, otherwise the star would break up, the disk omega must decrease with the decrease of r close to the star. That is, far from the star with the decrease of the radial distance r, the Keplerian angular speed omega increases, but the star cannot rotate with the Keplerian speed, otherwise it would break up. So, this angular speed has to decrease near the surface of the star, and therefore, omega will attain a maximum value near the star, and therefore, d omega dr must be 0 at some point, which is assumed to be r equal to r in here in equation 11 near the stellar surface. On the other hand, for the second case, as mentioned here, that is when the star is well inside the disk and the matter falls from the disk inner edge towards the star quasi radially, the torque at the disk inner edge is expected to vanish. It, however, may not happen exactly in reality, but it can be true more or less, and this would make d omega dr equal to 0. So, in either of these cases, d omega dr can be 0 at a point very close to the stellar surface, which is the disk inner edge r in. Thus, we justify this boundary condition d omega dr at r equal to r in equal to 0. The region between the star and the disk in which the flow deviates considerably from Keplerian is called the boundary layer. Now, from equations 8, 9 and 11, 8 that comes from the mass conservation, 9 that comes from angular momentum conservation, and 11 which is the boundary condition that we have just now justified. We get this value of C2 in terms of the accretion rate and the mass and the stellar mass. Substituting this in equation 9 as shown here and using equation 8 and 10, we get nu sigma equal to m dot by 3 pi into 1 minus r in by r to the power half. This is equation 13, and this is a very important equation which we get only after we considered the steady state disk criterion. This is important because the unknown parameters like nu and sigma is now eliminated from the equations, as they can be expressed in terms of the observable parameters, that is accretion rate m dot. M dot could be inferred from the observed luminosity, and R in, which could depend on the mass and radius of the central object. In case of neutron star, it could be radius, or in case the disk does not go till the neutron star or the black hole, it could be the mass of the neutron star or black hole. It could depend on the mass of the neutron star and black hole. This relation also shows that the accretion rate is greater for larger viscosity, which is expected because it is the viscosity that makes the incoming particles lose their angular momentum, and thus the particles are accreted. The viscous dissipation in the accretion disk causes emission from the disk, and the source of this emitted energy is the gravitational potential energy release. This viscous dissipation rate per unit volume of the accretion disk is mu r square d omega dr whole square. Integrating this over the disk thickness and assuming Keplerian angular speed, we get the rate of energy emitted per unit area of the disk from equation 13, which comes out to be 3 g m m dot divided by 4 pi r cube into 1 minus r in by r whole to the power half. This is equation 14. Therefore, the total power emitted from a disk extending from r equal to r in, that is the inner edge, up to infinity is L equal to g m m dot by 2 r in. Note that if a test particle falls from infinity to the radius r in, its gravitational, it will lose a gravitational energy of g m m dot by r in. This shows that for a steady geometrically thin accretion disk in Newtonian gravity, half of the gravitational potential energy, because there is a factor of half here 1 by 2, is emitted by viscous dissipation in the disk, and the rest half remains stored in the accreted matter as the kinetic energy and gets dissipated in the boundary layer. However, if the central accreting source is a black hole which does not have a hard surface, this energy goes into the black hole. It is expected that a geometrically thin Keplerian disk should emit like a black body. Therefore, the temperature T effective of R of the disk surface can be calculated from equation 14. Here, this can be equated with sigma t to the power 4 as we do for a black body, and we have to multiply this side with a half, because here we consider the entire energy from both the surfaces of the accretion disk that is emitted, but to calculate the temperature we have to look at one side. So, we multiply this with half. So, this will be 3 by 8 instead of 3 by 4, and we equate it with sigma t to the power 4, and we get the temperature T effective of the accretion disk as given by this formula given in this equation 16. Here sigma is the Stefan-Boltzmann constant, as the black body temperature varies with the radial distance, as can be seen from here. The temperature is a function of radial distance r. The spectrum from a disk is known as a multicolor black body. So, at a given radial distance from the central object, the spectrum is a single temperature black body, but we cannot usually spatially resolve an accretion disk, and we observe usually its entire spectrum, and that spectrum will be the sum of all the black bodies from various radial distances, and this is called a disk black body or a multicolor black body. And this is a typical disk black body or multicolor black body spectrum as shown here.